Okay, hello class. Let's proceed to our to the second part in this topic. Okay, previously we have learned about the concept of vapor liquid equilibrium, which is we have two phases for the as example for the binary system at given temperature and pressure. Okay, in determining or solving the vapor liquid problem, we have learned about there are a few simple model that can be used. First, we already apply the Ross law equation, and due to the limitation of Ross law, we gonna also introduce the modified Ross law. Then we have Henry law, and last today we gonna move to the determine the or solve the problem using the K value from the pistol chart. Okay, there are three types calculation that we have learned. First, we have the bubble point calculation, dew point calculation, whether we have dew temperature or dew pressure. Same goes to the bubble point. It gonna have bubble temperature or bubble pressure. And also today we will move to the flash calculation. So we have this is the type of the calculation in solving the VLE problem. Okay, in this part, we gonna move to the other VLE model. We should able to solve the problem by using the modified Ross law that we gonna take a look on the example related to the modified Ross law, and then how to identify whether that system exists the or azeotrope is exist or not. So we will perform this problem related to the isotrope and able to solve the VLE problem using the K value correlation. Okay, the last topic is flash calculation. We will learn about the definition and concept of flash calculation and how to perform the calculation using this flash. Okay, back to the modified Ross law. In vapor liquid equilibrium, there are two types of diagram that give us, or in order for us to solve the problem, whether we have the TXY diagram, which we fix the pressure, and we have the PXY diagram, and we fix the temperature. Okay, from this example, it gives the data of TXY diagram, and then we can plot the diagram using this given data. So we have temperature versus mole fraction. Okay, at this x1 equals to 0, it gives us the P2 saturation because x2 equal to 1. That means this is our saturation temperature for component 2, or second component here is nitromethane. And then we have also give us from the data we can obtain the saturation temperature for component 1. So that's mean we have S1 equal to 1 and S2 equal to 0. Okay, these are the Anton equation that can we determine the saturation pressure. Okay, if the involve the bulk T calculation, so we need to find the temperature, and bulk here means the liquid phases or liquid composition is given. So the question is, what is the S1 here? So S1 is the vapor phase for component 1, and then we need to define the temperature for B prime using the S1 at 0.6 and P at 70 kilopascal. So to start with, okay, we start with this by introduce the alpha. Alpha, okay, start with alpha equal to 1, which we know that alpha is equal to P1 or saturation pressure for component 1 over saturation pressure for component 2. And then we will proceed to find the, okay, by rearrange it, we can obtain the P2 saturation equal to P over X1 alpha plus X2. Okay, this is from this calculation here. Okay, you can insert the P2, okay, rearrange it, and then because we have this P1 over P2 saturation equal to alpha. So that's why we can get P2 saturation P over S1 alpha plus S2. And then we can use this by substitute P2 to get the temperature. And then finally, we can have a new alpha. Okay, how can we get this? Okay, we know that this is a ln P saturation. Okay, example, ln P saturation equal to A minus B over C plus temperature. So you can rearrange this. So since we have alpha based on the P1 saturation over P2 saturation, so it tends to have this ln alpha. Maybe we can have ln P over X1 alpha plus X2 equal to A minus B C plus D. So by using this, so we have P here. Okay, we can rearrange this to have ln alpha. Okay, this is 0 point this because we minus this. We have a given the saturation or Anton equation for both species. So 14.2724 minus 14.2043. So we can get 0.681. So ln alpha is P1 saturation over P2 saturation. So this is how you get this expression, and using that you can find new alpha by it perform the iteration on that. So we start with alpha equal to 1. Once you start alpha equal to 1, so we can get the new P2 saturation. So using, okay, this is our first equation. And then after that, we can get temperature from this. Insert the, okay, this is our second information from this iteration. And then we can insert this to this expression to get the value of alpha. So you will check, okay, whether you can, maybe you can check it, okay, because 1.88 is far, it's not too close to 1, so we need to provide another iteration using alpha equal to 1.88, and then we can get P2 saturation, and then you can stop your iteration. Okay, this is supposedly iteration 4. Okay, you can stop your iteration when you find the value is similar, and then we can determine the P1 saturation and Y1, the value of Y component 1 at vapor phase. So this is the way we can find the value of perform the about the calculation. Okay, the next example, we have two component or binary system, methanol and methyl acetate. Okay, the following equation given the reasonable correlation for the activity coefficient. Okay, this is the general equation to determine the gamma or activity coefficient. Okay, the correlation for A here is given. In addition, the following Anton equation provide the vapor. Okay, this is for component 1 and this is for component 2. Okay, where T is in Kelvin and then the vapor pressure is in kilopascal. Okay, by applying the modified Ross law, calculate the, okay, first we need to determine the pressure and the composition in vapor phase, and given temperature and composition in liquid phase also given here. And next question is to determine the temperature by given the pressure and the liquid composition in this question. So the answer also given to you. So what we need to do is maybe you can try it first, and then we will compare with the sample or the calculation after this. So let's try by your own first. Okay, the first you can start it. Okay, for A here, since temperature is given, we can determine the value of A, and then it gives us the value of activity coefficient for both a component. So let's take a look. So for A, and then we can get the activity coefficient, and then also we can get the saturation pressure for both a species. And then by inserting this, okay, this is another equation because we are using the modified Roth's law, and then you can get the value of pressure. And then using this correlation, you can get the value of species for both for both species in a vapor phase, because y1 plus y2 equal to 1. If the question or the temperature is given to you and the liquid phases is given, it's easier for us to apply or use all the given information to determine the pressure and vapor composition. But if the temperature is not given to you, so we need to perform the gas temperature, because we cannot consider the vapor or P saturation pressure to determine the temperature. Otherwise, we perform the iteration. So let's start here. By rearrange the Anton equation, so we can get the saturation temperature for component 1 and 2. And then we can use this correlation to obtain the temperature or gas temperature. Okay, using the gas temperature, we can determine the A. Okay, we can get the A, and then finally it gives us the value of gamma or the activity coefficient for both species. And then you can insert the value of T, and then to get the value of saturation pressure for both species. And then using this, you can correlate it to find the value of alpha. So inserting this, okay, we can get the value of P1 saturation. Okay, for the next, you can read because P, okay, this is our first, if not involve the modified Roth's law. So since the modified Roth's law is introduced the gamma, so we have one P1 saturation or gamma. So maybe I put the gamma first. Okay, I insert the gamma 1 P1 saturation plus S2 gamma 2 P2 saturation. Okay, and then you can rearrange. Okay, this is from P1 saturation or P2 saturation is this, because the gamma, okay, alpha is P1 over P2. So P2 saturation, you can use this correlation of alpha. We have P1 over P2. So by using this over all of this over P2 saturation. So you can get this over P2 saturation, and this is over P2 saturation. It turns to, you can cancel this, and remain as 2 gamma 2, and this is given to you is the alpha. So this is how you rearrange your equation here. And then after that, you can have a new P saturation and inserting this value to obtain the calculated temperature. And then you may refer to the gas temperature, whether it's similar or not. If not, you may use that this temperature as your gas temperature, and then perform another step of iteration, and then it gives you the calculated temperature. You can compare with the gas temperature, and that is also not similar. So you may proceed to the next iteration. Okay, and then we can get the value of A here, and then the gamma. So inserting the value of temperature to give us the value of saturation pressure for both species, and then using this correlation, you can get the value of alpha, and then inserting into this equation to give your new saturation pressure for component 1. And then we can determine the calculated temperature because the P saturation is given. So you may compare with the gas temperature. So the value is similar. So you may stop the iteration by finalize the temperature, and then it give you the y2 or y1 plus y2 equal to 1. So y2 equal to 1 over y1. Okay, next topic is determination of azeotrope condition at given temperature. Okay, in obtaining or in determining whether the azeotrope is exist or not, we use the relative volatility, which 1, 2, that's mean component 1, 2, 2, we have y1 over s1 equal, because we know that for the azeotrope is y1 equal to s1. So we can use this correlation to obtain this. Okay, example here for modified Rod's law, by replace the yi or y1, and then you can have this another correlation. So from this, we know that the ln or gamma can be obtained. So you may replace it. Okay, so example here at s1 equal to 0. So we can have, okay, ln y or gamma 1 equal to s, since s1 equal to 0. So s2 turn 1. So we can have exponent A. So if we have ln gamma 2 equal to or s equal to 1, so ln gamma 2 s equal to 0, so ln 2 equal to exponent A or y or gamma 1 equal to 1. So you may rearrange this, and then finally you can use this correlation or inserting this or gamma 1 to for the condition of gamma 1 to s1 equal to 0. So we have two different value to obtain. First at s1 equal to 0, s1 equal to 0, and second is s1 equal to 1. So you may insert this into the correlation, into this correlation. So for both here, so because we have s1, okay, so you may get s gamma 1 and also gamma 2. And then calculate the alpha 1 to at s1 equal to 0 and s1 equal to 1. So the azeotrope exists if we have gamma component 1, 2 at s1 equal to 0 is less or between, we have this between the gamma 1 to s1 equal to 1, or this is the within this range, or if we have gamma for component 1 to s0 s1 equal to 0, it should be higher than 1 or equal to or higher than alpha s1 equal to 1. That's mean the azeotrope exist. Okay, to more understand how to determine whether the azeotrope exists or not, we may proceed to the example. Okay, we have a binary system, and our first example 2.4. Okay, we have the binary system. The component one is methanol and second component is methyl acetate. Okay, the following equation provide a reasonable correlation for the activity coefficient. Okay, this is the general correlation that we have learned. So it given the correlation for A here, and then in addition, the following unturned equation also given for both species. Okay, by applying the modified Rock's law, calculate the azeotrope pressure and azeotrope composition for T also given. So once we know the temperature, since the temperature is given, so we can determine the value of A, and then if we determine the value of A, that's when we can determine the activity coefficient for both species as well as the saturation pressure. So you can obtain the A and P saturation. Okay, to solve this, determine whether not an azeotrope exists at the given temperature. So using this relative volatility, since we know that as in azeotrope, we have the same composition for both liquid and vapor. Okay, in general, okay, this is from the modified Ross law. We have y or equal to S1 gamma I or Pi saturation. Okay, therefore, since for the alpha, we can get this y over S over Si here. So we can get the alpha equal to gamma 1 P1 saturation over S2 P2 or gamma 2 P2 saturation. Okay, when we perform the correlate with the activity coefficient, okay, example, we have this is the general equation A S2 square. So if we have S1 equal to 0, so it comes to ln gamma 1 A. So S2 equal to 1. So we have gamma 1 equal to, or ln gamma 1 equal to A. So if we have S1 equal to 1, so using this ln gamma 2 S1 square. So we have ln equal to S1 square. So gamma 2 equal to exponent A. So using this, you can obtain the value of alpha. So because we have inserting this to get this, and then to inserting the gamma or the value of gamma to get the correlation of this alpha. Okay, and then we move to the next information given is temperature. So you may insert the value of temperature. It gives us the value of saturation pressure and alpha. And then finally, you can determine your alpha or not alpha. It gives the value of A here. And then finally, you can determine the value of alpha. Since to comply with whether the azeotrope does exist or not, there are two restrictions here. We have one, or S1 equal to 0 should be higher to 1, 2, S1 equal to 1, or if we have S1 equal to 0 is less than 1, alpha 1, 2, S1 equal to 1. So we have this value of 0 or 2.052 is higher than 1, higher than 0.224. So the azeotrope does exist in this system. This is our conclusion. Okay, the next question is to determine the calculate the azeotrope pressure and composition. After we define whether the azeotrope does exist or not, so we proceed to determine the azeotrope pressure. Okay, for azeotrope alpha equal to 1. So this is the restriction to comply with the to define whether the system does exist the azeotrope or not. And then because of alpha 1 component 1 2 equal to 1, so from previous alpha 1 2 we have gamma 1 P1 saturation over gamma 2 P2 saturation. So since alpha 1, okay, alpha here equal to 0, equal to 1, so we have P2 gamma 2 P2 saturation equal to P1 gamma 1 P1 saturation. And then once we rearrange P2 saturation equal to P1 saturation over P2 saturation equal to gamma 1 over gamma 2. That gives us this another expression, and then we can calculate the value of from this correlation. So P or azeotrope equal to gamma 1 azeotrope over P1 saturation or times P1 saturation. So by using this, you may insert to determine the value of gamma 1 at azeotrope. So by comparing or having the differentiate between the activity coefficient of component 1 and 2, so we can have another correlation. So this is we have ln gamma 1 over gamma 2 equal to A as 2 square minus A as 1 square. So you can expand this and to have only the 2 or A equal to A times 1 minus 2 as 1. So you can solve this ln gamma 1 over ln gamma 2 equal to A 1 2 as 1. And then you can get the value of S1 because we already defined the gamma 1 over gamma 2 from this value. And then finally, you can obtain the value of S1. So it gives us since to comply with the azeotrope S1 equal to Y1, so we can also conclude that the composition of azeotrope is also equal to 0.325. So you may insert this into correlation of ln gamma 1 equal to A as 2 square. It gives us the value of gamma 1. And then finally, you can determine the azeotrope pressure using this gamma 1 azeotrope times the P1 saturation. Okay, next how to solve the VLA problem using K value. Okay, the lightness of a species or its tendency to favor the vapor phase known as the equilibrium ratio or KY, or we call as K value. Okay, the correlation is KY or KI equivalent to YI over SI. So we also can rearrange it whether by using the Rod's law or modified Rod's law to replace it to having the KI equal to PI saturation over P, and for modified Rod's law we have KI equal to gamma I PI saturation over P. Okay, if the value of K is higher, so we're gonna have higher composition in a vapor phase, or known as the light component. If K value is lower, so we can have higher higher liquid component, or it gives us the heavy component. Okay, there are two methods to determine the K value by using the from the correlation of Rod's law and modified Rod's law, or from D-Pister chart. Okay, for the D-Pister chart, K value only depend on temperature and pressure. So we need to find the value of temperature and pressure before we can obtain the value of Ki. Okay, it's readily available for light hydrocarbon. And then there are two types of chart for the range of a lower temperature and higher temperature. And then the other things is if you have this, the species or the component is more than two. That means if in your distillation column that having more than two components, you can apply this D-Pister chart. Okay, let's take a look. Okay, these are the summary. We have the K value correlation with Ki equal to the component or the composition at a liquid phase over the composition in, or the composition of vapor phase over the composition in liquid phase. Okay, for the bubble point calculation, bubble, that means the S is given. So we need to determine the component or the composition in a vapor phase. So the rule is the summation of this component in vapor phase should be equal to 1. So opposite to the dew point calculation, that means the Y or the composition of vapor phase is given. So we can have the we should comply all the composition of a liquid phase should be equal to 1. So we can determine this based on the method using the Rod's law or modified Rod's law or D-Pister chart. Okay, this we call as D-Pister chart. So we need to determine the to have the value of pressure and temperature before we can obtain the value of Ki. So this is the value of Ki at the lower temperature. You can see is this chart can be applied from -70 to 20 degrees Celsius. And the next for higher temperature from -5 degrees Celsius to 200 degrees Celsius. So these are the component usually for light hydrocarbon. And this is if we have another unit of Fahrenheit. Okay, these are the guidelines to determine the or to solve the VLE problem using K value from D-Pister chart. Okay, for the VLE calculation, we have bulk P. That's mean we need to find P, and then the S is given or liquid phase is given. And then we need to perform the iteration to solve the bulk P until we can get the summation of vapor phase equal to 1. So for the dew P, we need to find P, and then the composition of vapor is given, and then perform the iteration until all the composition of a liquid equal to 1. So for the bulk T, we need to find the temperature, and then the liquid composition is given, and then perform the iteration until we can get the summation, the total summation of a vapor phase equal to 1. And then the last is to have the bulk T, the dew temperature. We need to find the temperature, and then the given is vapor composition, and perform the iteration until all the liquid composition is equal to 1. Okay, for the bulk P calculation, this is how you can perform if involve the bulk P calculation. So we need to guess the P first, and then to get the value or K value, because from the chart we need to have the information of P and temperature or pressure and temperature. So because we don't have the value of P, so we start with guess the value of pressure. So these are the component. Usually it's in for the light hydrocarbon, and if the component is more than 2, you can apply this chart or D piston chart. Okay, as I is given, and then Ki is obtained by guess or guessing the value of P, and then you may determine the Y here by using this correlation, because as Ki is obtained as well as the value of a liquid composition, and then if the summation is equal to 1, you can finalize your pressure and the composition. But if not, you need to restart your calculation by pick the largest Yi here. Okay, example, for each component, you pick the largest, the composition from T4 here and get the value of Ki. So the value of Ki you can get from this T3, and then based on that, determine the new Ki by using this correlation. Okay, for the DUP calculation, since we need to find the P, so we need to guess the value of P. Okay, the same procedure, but the opposite is this. Instead of previously submission of vapor phase, so we need to turn to the submission of liquid phase. Okay, please remember that if we involve, so we need to find the or the given is the Y, so the submission should be the opposite phases, so it turns to submission of liquid. So we move to the next. If involved bulk T, so basically we're gonna use the same procedure. So we need to guess the temperature, because we need to find this temperature. And then bulk T is about, that's mean the X is given, so we need to find it to ensure the submission of opposite phase, which is the vapor phase, is equal to 1. So if not, we need to proceed with this correlation. Okay, same goes to the duty. So duty, that's mean we need to find temperature, and then the due, that's mean the vapor is given, so the submission should be the liquid. So if not, proceed to this perform this correlation. Okay, let's take a look on the example. So we have a 3 component. So we have a few, okay, all the calculation. So we have bulk calculation, bubble point calculation, as well as the dew point calculation. So the composition also given to us. So you may try your own to obtain the value. Okay, let's take a look. So we have this line. So we at minus 60 Fahrenheit. So minus 60 Fahrenheit. So how can I choose whether to start with this, or maybe, sorry, how can I choose whether to which pressure should I maybe to start with this or to start with this? How can we start? Also, this we call as the gas pressure. So I start with 200 psi. So we can get the submission is higher. So since the submission is higher than 1, so I increase more the pressure. So I can obtain the pressure is lower than 1. So you can play around within this value. So I decided to proceed with 250. So it gives us 1.008. So it close enough. So no need to perform another iteration. Okay, for the due P, that's mean we need to find P, and then this given is composition in vapor phase. So the submission we need to find is the in liquid phase should be equal to 1. So proceed with the same method. So example, we start at P equal to 190. So the summation is 0 point or lower than 1. So I should increase the pressure, and then I can get the summation is higher. So it's close enough. So for the bulk T, find the temperature, and then we need to find or ensure that the summation of bulk here, that's mean the summation of vapor phase is equal to 1. If not, you need to perform another pressure, or you may use this correlation given in the summation. So you may follow this method. And then whereas for the bulk temperature, we need to find the temperature, and then we need to also ensure that the summation of liquid composition is equal to 1. And then you may stop if the summation is close enough to 1. Okay, and the last topic is flash calculation. Okay, for the flash calculation, okay, flash condition is a two-phase system where both liquid and vapor phases that are in equilibrium can be separate. If a liquid, that means we have the pressure is higher than bubble pressure, which will evaporate when lower. When we reduce the pressure at constant temperature, we know as known as the flash vaporization. Or for the vapor phase, that means we have the pressure is lower than U. Pressure will condense partially when we increase the pressure at constant temperature, known as the partial condensation. Okay, the flash calculation can be divided by 2, whether using the isothermal flash. That means the temperature and pressure are given, so we need to determine the phase composition, whether liquid or vapor phase. And then we have adiabatic flash. That means we need to determine the phase composition and temperature from the information of enthalpy. Okay, the flash calculation using the concept of distillation column. Okay, example here. In distillation column, we have the feed and also the overall composition. And then we have the vapor phase, or the area for the vapor. And we also have the composition for vapor, and then liquid, as well as the composition of liquid. So by performing the balance, we have L plus V, we can get the feed, right? Via flash. And then this is the overall balance. And this is component balance. So we can rearrange or L over V or equal to Z minus Y or over X minus Y. So this is from the rearranging this component balance equation. Okay, the concept of isothermal flash is here based on if we have pressure versus composition. So you can, we have F, okay, this is Fz, and this is for vapor and the liquid phase. So we have here, so that's why once we perform the balance, we can get the this arrangement. So that's why we use the concept of this distillation column to solve the problem related to the isothermal flash. So using the level rule, okay, we have this, okay, example here. So this is our F, and then this is our V and our liquid. So you can apply the level rule here. So to obtain this, okay, example here. So example to obtain the SY, so you can apply this rule. So L over V or AC, you can get AC over AB. This is over AB. Okay, you can apply this level rule to obtain the composition. Okay, next, or the continue for the flash calculation. If a system consists of 1 mole of non-reacting chemical, or F equal to 1 mole, is overall composition known as Zi, or L is the mole for the liquid with its the mole fraction known as, or denotes by, Si, or V is for the vapor and its mole fraction denotes by Yi. So this is the detail about it. Okay, we have the overall as I explained previously, and then by removing the liquid, because we need to in order for us to simplify our equation, so it turns to have this yi equal to zk, because by having the correlation that ky equal to ys. So using this, that's why we replace it to having the ki, or k value, and then this is our finalize. Once we finalize it, or using the summation of total I equal to 1. Okay, the isothermal flash calculation can be solved either by using the K value using the pistol chart, or Rock's law. If there is information about the saturation pressure from the Anton equation, so you can replace it to having this equation. Okay, the isothermal flash calculation require iterative procedure. By guess the value of V has to be made randomly but in the range from 0 to 1. So this is the summary in determining the flash calculation using K value. So we need to guess the value of V and get the value of K for each component. Okay, so Z and K and Y. So I will show to you the example after this for you to more understand. Okay, this is if using the Rock's law, and only applicable if the Anton equation of saturation pressure is can be obtained. So we can get all based on the Anton equation and then the summation. Okay, if no, we need to guess another value of V. Okay, let's refer to the example. Okay, but because there are too many range for the V, right? How can we decide the value of V? Okay, this is the guideline for you to perform or to start with the initial guess of the V. Okay, example, if we have the summation of Yi, okay, within this range, so this is your value. So if you find the value of a summation is 0. Within the 0.8 to 0.3, so the value of V should be 0.5 to 0.1. So you may perform the interpolation. Okay, you may use this guideline. Okay, let's take a look on example 2.6. Okay, for a mixture of, we have 3 components, and then the fraction also given at 10 degrees Celsius. What fraction of the system is vapor? So what's the vapor when the pressure is 13.8 bar? And what are the composition of equilibrium, vapor, and liquid phases? So we need to find the fraction in the vapor and the composition. Use the K value. Okay, since pressure and temperature and pressure are given, so the first column is to list the species, and then second the fraction from the information given. Okay, and then Ki, you can obtain it from the chart. So at 10 degrees Celsius, okay, let's refer to the chart. Okay, so we have temperature and pressure. This is Fahrenheit. Okay, you may refer to this at 10 degrees Celsius, and then 13. Okay, so you need to convert the unit, and then you may refer or proceed to the line there, and then you can obtain the value of ki, and then insert the value into this table. Okay, then you can start with guess the value of v. So example, you may choose any range from 0 to 1 for the value of v. Okay, example, I start with 0.35. So you can use this equation to obtain the yi. So, and then total up all the y for all the species, and then you can obtain this value 0.957. So using this guideline, so the value is 0.957. Y is 0.957. So the range is between, okay, so you may perform this interpolation 957, and then you can get the next value of v. Okay, example, once you perform, it has 1.018, so it's still not equal to 1. So 1, so you need to perform the interpolation. Next interpolation for another value is 1.018, and then you can get the value of v, and then after that perform your another iteration, so you can get your value of, if it reach the summation is equal to 1, so you can stop the iteration, and then your v here is 0.273. And then finally, using this correlation, you can get the value of si. So this is how we solve this the VLE problem using the pixel if involved the flash calculation. Okay, in summary, we have the VLE type calculation, bubble point calculation, and then we have dew point calculation, and also the flash calculation. So for bubble point or bubble pressure, the information known is temperature and the S. Because bubble, that's mean we have the information of S. So for this dP, we have this. We need to find T, then we need to find P, and then the temperature is given, as well as the vapor phase, the composition of vapor phase. Okay, for flash point or flash calculation, the known information should be pressure and temperature, because we need to find the value of K or K value. And then the information need to compute is, okay, these are the list depending on the type of the VLE problem. And then these are the criteria that you should fulfill. Okay, example, if involved with the bubble pressure, so we need to have the submission of the opposite information here. So the opposite here is vapor, the submission of the vapor equal to 1. And then same goes to the rest of the other VLE calculation. So for based on the aspect of the convergence, so the simplest is this BP, and then the most difficult is flash point, because we need to perform the iteration for the volume, or we have this pressure, so it depends on the given information. Okay, these are the summary in this topic for vapor liquid equilibrium. Okay, we already defined the base diagram, whether using the 3D or 2D diagram. Okay, for both these, you should able to define the bubble point, or it give the bubble line if we combine the point of the bubble. So we have the bubble point, and then what is a definition or the concept of dew point, and also the tie line. So for the tie line, we can have two composition between the liquid and vapor. So the next is the to solve the problem related to the PLE using the PLE model, the Ross law. What is the Henry law? So for the Ross law, we have the ideal solution and also ideal gas. What is the limitation of the Ross law? So we have the Henry's law, which if we have the concentrated of one species, that we can ignore another species using the Henry's law and the modified Ross law to modify it from having the ideal solution to introduce the activity coefficient into the system. And then last is the K value relate to the flush calculation. Okay, K value, that's mean we need to define our PI and TI to obtain the value of K from the pistol chart, or you can solve it using the flash calculation. Okay, and then as to test your understanding, okay, first differentiate between two types of the flash calculation and give the provide the example in the industry. Okay, we will end our session. Okay, and then the next topic we will learn on the new chapter, which is the related to the solution thermodynamic, that we will cover on the partial properties, fugacity, another properties to overcome the limitation from the previous chapter that we have learned, as well as the access property. So thank you for your attention, and I see you for the next topic. Bye.